Hi everyone, welcome to GoClasses. So this is the last lecture in graph theory. We have seen all the concepts. We have seen the concept of coloring, chromatic number, independent set, degree of a graph, degree of a vertex, okay, directed, undirected graph, planar graph, Euler, Euler and Hamiltonian circuits. So basically many concepts we have seen: vertex cover, edge cover, matching, okay, click number, connectivity, cut vertex, vertex cut, okay, connectivity number. So basically many concepts we have seen, and this is the final lecture. In this lecture we will study these two concepts. We will study what is this connected, what is this strongly connected component in directed graph, what is this concept, and what is this concept adjacency matrix and adjacency list. Okay, adjacency matrix and adjacency list. So this concept we will study. So let's start now. Before we start, let's see for undirected graph, what is connectedness and what are components. You already know. If you have undirected graph, then what are the components? Components are like islands. I told you, components are like islands. So this is an undirected graph. In this graph, tell me how many components are there. Tell me how many. What is the number of components? What is the number of components? Number of components, or we call them number of connected components. See, this is same as number of connected components. Component is same as number of connected, because every component is a connected. Every component is connected, right? Every component is a connected graph. Like this component, this is the component and this is connected graph. So I can say number of connected components. So both things are same. Remember, both things are same because every component is a connected graph. Every component is a connected graph. Okay, every component is a connected graph. So I can say number of connected components is 2. So this is the concept for undirected graph. You know, for undirected graph, this is very easy. For undirected graph, what is a component? Component is like, I can say component is like a island. We have already seen this. Okay, so for connectedness in undirected graph, this is straightforward. I can say like this graph. If you look at this graph, just look at this graph. If you look at this graph, then you can notice that this and this, they are not connected. You can clearly see this and this, they are not connected. You can clearly see there is a gap. There is a gap. Okay, they are not connected. So this is the idea. Very simple. So I can say a graph that is not connected is obviously disconnected in components. So this is a component. This is a component. So total 2 components you have. Okay, so this is the definition. You know, when can I say graph is connected? What is the definition of connected graph in undirected? When you have undirected graph, for undirected graph is connected if for every pair of vertices there is a path. Between every pair of vertices there is a path, and I can say else the graph will be disconnected. Okay, so for example, this graph, look at this graph. This graph is disconnected, but if you look at this graph is connected. Okay, in this graph, between every pair of vertices there is path. Whatever 2 vertices you take any 2 vertices, there is a path between them. So this is a connected graph, and this is a disconnected graph because there is no path between a comma f. There is no path. And you can notice in this, so this is disconnected. In this, how many components you have in this graph? How many components? Total 2 components you have, this and this. Total 2 components. And in this graph, how many components? 1 component. Okay, so you can notice a graph is connected if and only if there is 1 component. You know this concept. Okay, for undirected graphs, I am talking about undirected graphs. So for undirected graphs, you can notice that a graph is connected. I can say a graph is connected if and only if number of components is equal to 1. If and only if number of components is equal to 1. Okay, and a graph is disconnected. Similarly, I can say a graph is disconnected if and only if number of components is greater than or equal to 2. I can say number of components will be greater than or equal to 2. This is the definition. Okay, so this is the concept, very simple concept. You know, in this graph, how many components you have? In this graph, total how many components? 3 components you have. So you can notice this is a component, this is a component, this is a component. So total 3 components you have in this graph. Okay, so connected component, that is basically maximal connected subgraph. You know this concept. Okay, what is a connected component? What is a component? What is a component? Component is basically maximal connected subgraph. Maximal connected subgraph. Maximal connected subgraph. This we have already seen in the previous lectures. Okay, so these components are like islands, I can say, in the undirected graph. Okay, these components are like islands. I can say this is an island, this is an island, this is an island. Okay, like this. Now let's see in this graph how many components. Total how many components? Total 2 components you have in this graph. Okay, so very simple. In this graph we have total 2 components. So this is a disconnected graph. Now let's move on for directed graph. For directed graph, how can I say, okay, what is connected and what is component? How to define this? For directed graph, see, this is different. This is very different. For directed graph, this is actually different. If I give you this directed graph, A, B, C, if I give you this directed graph, okay, consider this graph. What do you think? Is this connected? Is this graph connected? What do you think? Is this graph connected? What do you think? Think about it. Please think about it. Do you think this graph is connected? So remember, for directed graph, okay, like, okay, for undirected graph, you will think, okay, yeah, this is connected. It seems like this is connected, right? It looks like that this is connected because it looks like one part. Yes or no? It looks like one part. It looks like one island. Yes or no? It looks like one island. Okay, it looks like one island. Similarly, this graph, is this graph connected? What do you think? This graph, is this graph connected? Just think about it. Is this connected? Let me tell you, the answer is no. Let me tell you, the answer is no. Because, okay, for directed graph, see here, if you notice, this graph, this is a directed graph. First of all, remember, this is a directed graph. Okay, this is a directed graph. In the directed graph, you can notice one thing, that we cannot go from C to A. Okay, there is no path. I can say there is no path. There is no path from C to A. You cannot go from C to A. There is no path from C to A. And because there is no path from C to A, so this directed graph, this is not connected. This directed graph is not connected. Okay, so because there is no path from C to A, we have no path from C to A. So remember, it looks like this is one part. See, where is, I know some of you might be thinking, sir, this is one part. This looks like one island. It looks like one island. It looks like one part. Okay, one part. It looks like one entity. It looks like one entity. But remember, this is not how connectedness is defined for directed graph. For directed graph, we don't define connectedness like this. Yes, this is one entity. I know. This is one entity. This is one island. I know. But remember, still this is not connected because you cannot go from C to A. There is no path from C to A. So that is the reason this is not connected. Actually, let me tell you one more thing. Actually, for directed graph, this word we don't use. We don't use this word. We use this word, that this is not strongly connected. This word we use, strongly connected. This word we use, okay, strongly connected. We don't use this word. We don't use this word, but we use the word strongly connected. Okay, but remember, by default, connected and strongly connected, they are same thing. For directed graph, by default, these are same thing. For directed graph, there is a concept of, we will study, don't worry, we will study. Okay, there is a concept of strongly connected components, strongly connected components, or I can say strongly connected graph. Strongly connected graph. Okay, strongly connected graph. Remember, by default, strongly connected graph, and I can directly say connected graph. Both are same. By default, when I say connected graph for directed graph, then that is same as strongly connected graph. So, okay, so this graph, if you notice, this graph is not connected. This graph is not connected, or I can say this graph is not strongly connected because we cannot go from C to A. We cannot go. Okay, so let's define it. Now let's see one by one. Don't worry, you will understand. Don't worry. Let's define first. Let's see for two vertices. Let's define how they are connected. Okay, two vertices are connected, or I can say two vertices are strongly connected. By default, connected means strongly connected. Remember this point. Okay, remember this point, that for directed graph, by default connected, by default this connected automatically means strongly connected. By default connected means strongly connected. So even if I don't say strongly connected, by default connected means strongly connected. Okay, by default. Now let's see this. See this definition. In a directed graph, your graph is directed. In a directed graph, two nodes are connected, or I can say two nodes are strongly connected if and only if there is a path from U to V and there is a path from V to A. Remember, there is a path from U to V, and there is a path from V to U. Then we will say, means I can say there must be a path from U to V and there must be a path from V to U. This must happen. This must happen. This must happen. There must be a path from U to V and there must be a path from V to U. This must happen. In this situation, if this situation happens, then we will say that U comma V are connected, are strongly connected, are strongly connected. Okay, then we will say that they are strongly connected. Means you can go from U to V, you can go from V to U. So tell me, in this graph, okay, which two vertices are strongly connected? So find out, like, okay, strongly connected vertices. Which two vertices are strongly connected? Let's see. Let's see which vertices are strongly connected, or I can say which vertices are connected. Can I say vertex A comma, okay, can I say vertex A comma B are connected? Please tell me. Can I say vertex A comma B? Can I say they are connected? You can go from A to B. Can you go from B to A? Yes, you can go from B to A. You can go from B to A. Okay, so you can notice, you can go from A to B. You can go from B to A. Okay, so I can say yes, these are strongly connected. These are connected. What about A comma D? What about A comma D? Yes, you can go from A to D. You can also go from D to A. So they are also connected. What about this A comma F? What about A comma F? Tell me about A comma F. They are no, because you can go from A to F. You can go from A to F, but you cannot go from F to A. Okay, you cannot go from F to A. What about B comma D? What about B comma D? Yes, because you can go from B to D and you can go from D to B. Okay, so these are also connected. What about these, like F comma H, or I can say F comma H? What about them? F comma H. You can go from F to H, but can you go from H to F? Can you go from H to F? No, so these are also not connected. F comma H, these two vertices are not connected. These are not strongly connected. What about G comma H? No, because you can go from G to H. There is a path from G to H, but there is no path from H to G. Okay, what about this F comma G? F comma G, again no, there is a path from F to G, but there is no path from G to F. So these are also not connected. These are also not strongly connected. Please let me know if anyone has any doubt. Let's see this B comma F. What about this B comma F? Okay, there is a path from B to F. There is a path from B to F, but there is no path from F to B. So these are also not connected. These are also not strongly connected. So the definition is very simple. Two vertices are strongly connected. Two vertices are strongly connected if you have a path from U to V and you have a path from V to U. Okay, so then we will say that they are connected, or I can say they are strongly connected. Now one interesting question I will ask you. Very nice question. See this. In a directed graph, let's define a relation on set of vertices. Let's define a relation. We are defining a relation on set of vertices. We are saying that vertex A is related to vertex B if and only if A comma B are strongly connected. Okay, means two vertices are related. These two vertices are related if and only if they are strongly connected. Tell me one thing. Is this reflexive? Is this relation reflexive? Is this relation symmetric transitive equivalence relation? What is this? Okay, let's check it out. Let's check it out. Let's check it out on this graph. On this graph, let's check it out. Tell me, can I say A comma A? Can I say they are connected? Can I say they are strongly connected? Can I say they are strongly connected? Tell me. See, strongly connected. Strongly connected. Okay, strongly connected pairs. Tell me, A comma A, are they strongly connected pairs? Yes, because very trivial. These are trivially. Okay, trivially. You can go from A to A. Trivially you can go. Like you, okay, just don't walk. Okay, there is a path from A to A. Trivial path, I can say. Trivial path you have. Trivial path. Path of length 0. Path of length 0. Trivial path you have from A to A. Okay, so yes, they are strongly connected. Next, what about C comma C? What about C comma C? Again, the same thing. Yes, trivial path. Okay, there is a trivial path means length 0. Trivial path length 0. Okay, next, what about A comma B? A comma B. You can notice there is a path from A to B, and you can notice there is a path from B to A. There is path from A to B, and there is path from B to A. So I can say yes, they are also strongly connected. What about B comma A? What about B comma A? Yes, they are also strongly connected. Okay, because there is a path from B to A, there is path from A to B. Okay, next, tell me. So you can notice that A comma B, okay, they are strongly connected, and you can notice that you can also notice that B comma D are also strongly connected. Okay, A comma B is strongly connected. B comma D is also strongly connected. You have path from B to D. You also have path from D to B. So okay, these are connected. You can notice that automatically implies that A comma D are also strongly connected, right? Yes or no? Automatically implies that A comma D are also strongly connected. You have path from A to D. You have path from D to A. So they are also strongly connected. So this is the idea. I can say that on vertices, if you define this relation, then can I say this is reflexive? Yes, this is reflexive. Why this is reflexive? Remember, your graph, you have a directed graph. You have a directed graph G, V, comma E. Okay, you are defining a relation R. This relation R you are defining on set of vertices, and you are saying that a vertex U is related to vertex V if and only if, okay, there is a path from U to V and there is a path from V to U, means they are strongly connected. Okay, so this is the question. Now you can notice this R is reflexive. This relation, if you notice this relation, this is reflexive. This is reflexive. Why this is reflexive? Because I can say that A is related to A trivially. Okay, I can say A is related. I can say A is connected to A trivially. Okay, path of length 0. Path length 0. Path length 0. Okay, next, are they symmetric? This relation, is this symmetric? Is this relation symmetric? And the answer is yes. The relation is symmetric also. Because see, very simple. If A comma B are strongly connected, then B comma A are also strongly connected. Very simple. It means you can go, there is a path from A to B, there is a path from B to A. It automatically means there is a path from B to A, there is path from A to B. So you can notice, if this happens, I can say, if this happens, or I can say that if A is related to B, it means A is related to B, means if they are strongly connected, then B comma A is also strongly connected. What about transitive property? What about transitive property? Yes, transitive property is also true. Very simple. See, if A comma B are strongly connected, B comma C are strongly connected. Okay, if these are strongly connected, then what it means? See, then what it means? It means there is a path from A to B. Okay, there is a path from B to C. There is a path from B to A, and there is a path from C to B. So you can notice there is a path from A to C. You can clearly see there is a path from A to C. There is path from A to C. There is path from C to A. There is path from A to C. There is path from C to A. So yes, okay, they are also strongly connected. If A comma B are strongly connected and B comma C are strongly connected, then A comma C is also strongly connected. Very simple concept. Because you can notice that, okay, you can notice there is a path from A to C. This is the path from A to C, and this is the path from C to A. So this is transitive also. So I can say this is equivalence relation, reflexive, symmetric, transitive. So this is a equivalence relation, correct? Okay, this is the equivalence relation, very simple. So yes, all these properties are there. Okay, so this is equivalence relation also. Now let's find out equivalence classes. If this is equivalence relation, then you find equivalence classes. Let's find equivalence classes. Let's find them. Let's find equivalence classes. Okay, let's find them. So in this graph, let's find the equivalence classes. What do you think? What are the equivalence classes in this graph? What do you think? In this graph, what are the equivalence classes? Okay, so let's find equivalence classes. Equivalence classes. Find out the equivalence classes. See, what is the equivalence class of A? Tell me the equivalence class of A. Please tell me the equivalence class of A. Equivalence class of A means to which A is related. To which A is related. See, A is related to A. You can notice that A from A to B and from B to A. You can notice A comma B are strongly connected. A comma B are strongly connected. A comma B are strongly connected. A comma D are strongly connected. Okay, there is a path from A to D. There is a path from D to A. So they are also strongly connected. What about C? Can I say A comma C are strongly connected? Can I say A comma C are strongly connected? A comma C. Can I say they are strongly connected? A comma C. You can notice, yes, they are strongly connected. You can notice they are strongly connected. You can go from A to C. There is a path from A to C. Notice there is a path from A to C. Notice there is a path from C to A. There is a path from C to A. So there is path from A to C. There is path from C to A. So finally, only one equivalence class you will get. Only one equivalence class. So for this graph, I can say for this graph, only one equivalence class. For this graph, only one equivalence class. Let me tell you one thing. What this equivalence class tells you? This tells you that every two vertices are strongly connected. Yes or no? Agree? Every two vertices are strongly connected. Every two vertices, if you take any two vertices, are strongly connected. Every two vertices are strongly connected. Every two vertices, whatever two vertices you take, those two vertices are strongly connected. So this is a strongly connected graph because every two vertices are strongly connected. So this graph is connected graph, I can say, because every two vertices are strongly connected. So that is the reason this graph, we call it a strongly connected graph. This graph is strongly connected. Okay, so actually, let me tell you one more thing. Let me tell you one more thing. In this graph, if you notice, there is only one equivalence class. This equivalence class is called a strongly connected component. Okay, let me just tell you that this equivalence class, every equivalence class, this equivalence class, every equivalence class of this strongly connected relation, strongly connected relation. So this relation that we have defined, okay, this relation that we have defined, right? So every equivalence class of this relation is called strongly connected component. Strongly connected component. That is called strongly. Don't worry, this will be clear. Don't worry. If you have any doubt with example, this will become clear. So do not worry about it. Now let's see. So okay, anyway, there is a mistake in this. There is a mistake in this. So there is only one strongly connected component. In this graph, there is only one strongly connected component because every two vertices, if you notice every two vertices, they are strongly connected. So this slide is actually wrong. Now let's see. In this graph, on this graph, let's apply. How many equivalence classes are there? On this graph, let's apply let's find out how many equivalence classes. Find out equivalence classes. Let's find out equivalence classes. What are the equivalence classes? Let's find out the equivalence classes for this graph. So let's find out, okay, equivalence classes. So what is the equivalence class of A? Please tell me what is the equivalence class of A. What is the equivalence class of A? See, equivalence class of A will have A. And you can notice one thing. Just notice one thing. Just notice one thing. This is a loop. If you notice, this is a loop. This is a loop. This is a loop. If you notice, it means there is a path from A to B. There is a path from B to A. There is a path from A to D. There is a path from D to A. There is a path from A to C. There is a path from C to A. So between any two vertices, there is a path. I can say here in this, every two vertices are strongly connected. There is a path from B to C. There is a path from C to B. So you can notice they are on a cycle. Okay, they are on a cycle. So I can say yes, they all are strongly connected. Okay. Oh, every pair here, every pair is strongly connected. What about A comma F? Tell me, what about A comma F? A comma F are not strongly connected. Yes or no? A comma F is not strongly connected. A comma G is not strongly connected. A comma H is not strongly connected. There is a path from A to H, but there is no path from H to A. So they are not strongly connected. So this is the equivalence class of A. We got equivalence class of A. Okay, and this is also equivalence class of B. This is also equivalence class of B. This is also equivalence class of C. This is also equivalence class of D. This you already know. Okay, so this equivalence class we got. Now let's find out equivalence class of F. What that will be? Equivalence class of F. That will be only F. That will be only F, because remember, okay, you can notice F comma H are not strongly connected. There is a path from F to H, but there is no path from H to F. There is path from F to G, but there is no path from G to F. So this is the equivalence class of F. What is the equivalence class of G? Equivalence class of G, that is G itself. And what is equivalence class of H? That is H only. That is H only. So in this, you can notice 4 equivalence classes we have. How many? 4 equivalence classes we have. Okay, every equivalence class. So okay, every equivalence class is basically a strongly connected component. You know this. So this is a strongly connected component. 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 Okay, because you can notice that this is a strongly connected component. This component in this area, look at this area. In this area, everyone is strongly connected to everyone. In this area, everyone is connected to everyone. Everyone is strongly connected to everyone. So this is strongly connected component. This is a strongly connected component. This is a strongly connected component. Tell me, is this a strongly connected component? Tell me, is this a strongly connected component? No, because G comma H are not strongly connected. There is path from G to H, but there is no path from H to G. Okay, so this is not a strongly connected component. So remember, every equivalence class is, I can say every equivalence class is basically a strongly connected component. Okay, so this statement we have already seen that every equivalence class of this strongly connected relation is a strongly connected component. Now you can easily find out strongly connected components. So what is a strongly connected component? Tell me, what is the definition of a strongly connected component? What is that? A strongly connected component is simply a set of vertices. This is the definition. A strongly connected component, SCC. What is that? A strongly connected component. So I can say this is a set of vertices. Please note this definition. Read the definition. Read the definition. What is a strongly connected component? A strongly connected component. This is a set of vertices. Remember, this is maximal set of vertices. This is maximal set of vertices, okay, which are strongly connected to each other. So this is the maximal set of vertices. This is a maximal set of vertices such that any two vertices are strongly connected. Okay, any two vertices, every pair of vertices is strongly connected. Every pair of vertices, there is path from U to V, there is path from V to U. This is the definition. Okay, so maximal set of vertices which are strongly connected. This is the definition of strongly connected components. Very simple definition. So you can notice, if this is SCC, if I say If I say this is SCC, A, B, C, D, if I say, okay, for example, if SCC is this, a strongly connected component is this, what it means? Tell me what it means. It simply means that, it simply means there is a path from A to B, there is a path from A to B, and there is a path from, okay, B to A. Similarly, there is a path from A to C, and there is path from C to A. Similarly, there is path from B to C. You can note this is the path from B to C. So there is path from B to C, and there is path from C to B. You can notice this is the path from C to B. And similarly, there is path from C to D, and there is path from D to C. So this is the idea. You can notice. Now, okay, is there any path from A to D? Yes. This is the path from A to D. This is the path from A to D. And you can note this is the path from D to A. So between any two vertices, okay, between any two vertices you take, there is a path. Every two vertices you take, there is two-way path. Any two vertices you take. And remember, if this is SCC, then this is maximal also. If this is SCC, then this is maximal also. What it means? This is maximal also. What this means? This means there is no other vertex. This means there is no other vertex. This means there is no other vertex. There is no other vertex E. There is no other vertex E such that this will happen. Such that this will happen. There is no other vertex such that this will happen. Okay, so this will not happen. Let's see this example. In this, you can notice, is this a strongly connected component? Please understand, tell me. Is this a strongly connected component? Yes. Okay, yes, you can notice this is a strongly connected component. This is a strongly connected component. This is also a strongly connected component. What about these two? What about these two? What about these two? Are they strongly connected? No, they are not strongly connected. They are not strongly connected because there is path from this to this, but there is no path from this to this. So in this, how many strongly connected components? Number of strongly connected component is 2. Is this a strongly connected component? Is this a strongly connected component? No, a strongly connected component is maximal. Remember, this is not a strongly connected component. This is not a strongly connected component because this is not maximal. Because this is not maximal. Okay, this is not a strongly connected component because this is not maximal. So number of strongly connected component is 2. Similarly, this is not a strongly connected component because this is not maximal. You must take maximal. You must take maximal. Okay, always take maximal. These are strongly connected vertices. A, B are strongly connected vertices, but this is not a strongly connected component. Please understand. A, B are strongly connected vertices. They are strongly connected, but this is not a strongly connected component. A, B are connected. That is fine. A, B are connected. Very good. No problem. But this AB, this is not a strongly connected component. Is this clear? Component. This component. Component means this should be maximal. Let's see this graph. In this graph, how many you see? How many components are there? A, B, C, D, E, F, G, H. Okay, let's see one by one. How to find out? Okay, please understand this method. What I'm going to tell you, please understand this. First, you find out what is the strongly connected component in which A is there. So first you find out a strongly connected component to which A belongs. To which A belongs. Find out the strongly connected component to which A belongs. So you can notice there is a cycle here. If you notice there is a cycle here. See, there is a cycle. There is a cycle here. So definitely these are in the, okay, so definitely these we have A, B, C, D. Can I put E? Please tell me, can I put E? You can notice that there is no path from E to A. There is no path from E to A. We don't have any path from E to A. You can notice there is no path from E to A. There is no path from E to A to F. sorry, F to A. So okay, so this is the strongly connected component to which A belongs. So this we got. Now forget about it. This is what we got. You cannot add anything more. Remember, you cannot add anything more. So this is done. Now look at the remaining graph. Look at the remaining graph. Okay, strongly connected component of E. What is the strongly connected component of E? That is E comma F. That will be E comma F. You cannot add anything more. You cannot add anything. Okay, you cannot add anything more. So this will be your, okay, now forget about it. Next, you can notice there will be G, next there will be G, and next there will be H. Next there will be H. So total 4 components, connected components you have is in this graph. These are the 4 strongly connected components. Is this clear? Anyone has any doubt in this? Let's see another question. Let's see this another question. If I change this arrow, if I modify this arrow, let me modify this arrow to this side. Let me modify this arrow to this side. Now tell me the answer. Tell me the answer now. Let's find out the strongly connected component to which A belongs. Okay, so you can notice this A, B, C, D, because there is a cycle. See, there is a cycle. So A, B, C, D, A, B, C, D. Now let's see. Can I say, see, there is a path from A to E. Can I say there is a path from E to F, E to A? Yes, E also will be included. Now E also will be included. F also will be included. E comma F, they will also be included. Yes or no? Now E comma F also will be included because there is again a cycle. See, there is a cycle. See, there is a cycle. See, there is a cycle. So you can notice that this is the component. So finally, I can say that this component you got this component. This component you got. Okay, one component, and the remaining is this component, this component. So number of strongly connected components, that is 3. Okay, so very simple. This concept is very simple. Let's find out this question. Draw a 3-vertex graph with one strongly connected component. Can you do this? With one strongly connected component. Only one strongly connected component you must have. So you can draw this graph. A, B, C, this graph. In this graph, you only have one strongly connected component. In this graph, number of strongly connected component is only 1. Because you have this cycle. You have this cycle. So you can notice this is the strongly connected component. Number of strongly connected component is 1. Okay, 2 strongly connected component. Can you draw a graph which has 2 strongly connected component? Can you draw a graph? A, B, like this, C. Okay, so in this, how many strongly connected component you have in this graph? Number of strongly connected component, that is 2. Okay, number of strongly connected component is 2. This is a strongly connected component, and this is a strongly connected component. 3 strongly connected component. What should be the graph? A, B, C. This graph will work. Yes or no? This graph will work. This graph will work. You can check it out. This graph will work because you can notice there is path from A to C. There is no path from C to A. There is path from A to B. There is no path from B to A. So finally, in this graph, this is a strongly connected component. This is a strongly connected. This is a strongly connected component, and this is a strongly connected component. So number of strongly connected components is 3. Okay, so like this. Yeah, that is also fine. 3 disconnected. This is also fine. Okay, how many for this graph? For this graph, how many strongly connected component? Number of strongly connected component is 3. For this graph, how many strongly connected component? A, B, C. How many strongly connected component? Number of strongly connected component is again 3. Is again 3. And okay, for this graph, how many strongly connected component? A, B, C. For this also, number of strongly connected component is 3. Is this clear? Here you have only 3 strongly connected components in this. This is the strongly connected component. This is the strongly connected component. This is the strongly connected component. So is this concept clear? Strongly connected component. The concept of strongly connected component. Remember, this must be maximal. Please understand, strongly connected component, this should be maximal. Many students make this mistake. This should be maximal. Okay, maximal. Okay, and basically every pair of vertices, connected, strongly connected. Okay, every pair of vertices is strongly connected, and this must be maximal. So if I give you this graph like A, B, C, D, E, this graph if I give you, then tell me how many strongly connected components, number of strongly connected component, how many? Very simple. Find out. Okay, this A is strongly connected to what? This A is strongly connected to whom? This is strongly connected to A. So you can notice this is strongly connected to B also. There is a cycle. There is a cycle like this. There is a cycle like this. So you can notice that these vertices A, B, D, E. Okay, so this is strongly connected. This is a strongly connected component. I can say this is SCC, strongly connected component. And there is another strongly connected component, that is C. So you can notice this is strongly connected component, and the remaining vertices, this is a strongly connected component. So this is your S1, this is your S2. Okay, so very simple. The concept is very simple. Remember one more thing, please remember this DE is this strongly connected component. This DE, this is not a strongly connected component because this is not maximal. This is not a strongly connected component. This component is not strongly connected. Let's see this graph, this question, and this is very interesting question. Before this, let me ask you another question. Before this question, let me ask you, if you have an undirected graph, let me ask you this question. Let's assume you have undirected graph. You have undirected graph G, in which, okay, you have undirected graph G in which you have number of vertices and number of components. Let's assume your graph is undirected. Let's assume number of components is K. Now tell me, okay, if, okay, let A comma B are two vertices. You have two vertices in this G. We add this edge. Okay, like there is no edge between them. Let A comma B be two vertices such that they are not adjacent. A comma B are not adjacent. Let's assume they are not adjacent, means there is no edge between them. They are not adjacent. Now we add this edge. Now we add this edge. Now we add edge AB. This edge AB we add in G. Then tell me what will be the number of components. What can you say about number of components? Remember what we are doing? What we are doing basically you have undirected graph. In that undirected graph, you are adding one more edge. You have undirected graph plus one more edge. Plus one more edge you are adding. Only edge you are adding between existing vertices. Plus one more edge you are adding. Okay. Then if you do this, then what can you say about number of components? What can you say about number of components? Very simple. Number of components, either it will remain unchanged, either it will be K or it will be K minus 1. Either it will remain unchanged or it will reduce by 1. Very simple. Very simple. Either it will be K or it will become K minus 1. For example, consider this graph. A, B, C, D, E, F. Consider this graph. This is your graph G. Now, if I add this edge, okay, add one edge. What you do? Add one edge. So in this graph, number of components is 3. If you notice, let's add one edge. If I add this edge, then number of components is what? Then number of components, that is still 3. Yes or no? If I add this edge, number of components, that is still 3. Number of components, that is still 3. If I add this edge, okay, instead of this, if I add this edge, okay, let's not add this edge. Now let me add this one. This edge let me add. Now what will happen? Now what will happen? The number of components, the new number of components, that is k minus 1. That is 2 now. So this is the idea. Okay, if you add one edge, very simple. In undirected graph, if you add one more edge between the existing vertices, then either the number of components will remain unchanged, or it will reduce by exactly 1. Either this will happen or this will happen. Okay, very simple. Either this will happen or this will happen. Now, the same question, let me ask for a strongly connected component. So you know the definition. A strongly connected component is maximal set of vertices such that any two vertices are strongly connected, mutually reachable. This is the definition of a strongly connected component. Okay. Now the question is saying that on adding one extra edge, an edge which is previously did not exist, to directed graph, the number of strongly connected component, can it increase? Please tell me, can it increase? Is it possible that it can increase? The number of strongly connected components, can it increase? You are adding one edge, can it increase? It cannot increase. Very simple concept. You have a directed graph, a very simple. You have a directed graph G. In this directed graph G, let's assume number of strongly connected component. Let's assume that is 4. Let's assume you have 4 components. Okay, let's assume this is S1. Let's assume this is S2. This is S3. This is S4. Now, if you add one edge, for example, if you add one edge like this, okay, if you add one edge, whatever edge you add, can you increase the number of components? Like basically, if you add one edge, by adding one edge, will they become less connected? Will they become less connected by adding one edge? Can they become less connected? They cannot become less connected. Very simple. So if you add one edge, by adding one edge, they will not become less connected, right? Okay, adding one edge does not make it less connected. Adding one edge cannot. Adding one edge, you are adding extra. You are adding extra edge. So adding one edge does not make it less connected. Does not make it less connected. Less connected means a strongly connected component cannot increase. Okay, does not make it less connected. Very simple. Okay, if you add one edge, then it will not make it less connected. I can say number of strongly connected component cannot increase. Cannot increase because you are adding one edge, then it cannot increase. Okay, very simple. Now, what about this? So this, okay, cannot increase, that is fine. Okay, cannot increase. Cannot increase, this is correct. This is correct. Cannot increase. Very good. How much it can decrease? Can it remain unchanged? Tell me, can it remain unchanged? May remain unchanged. May remain unchanged. Is it possible? Can it remain unchanged? Yes, it can remain unchanged, right? Okay. Yes. So if you have a graph G plus one edge, then okay, you can notice that it can remain unchanged. Like for example, if you have this graph A, B, C, this graph, consider this graph G. In this graph, let me add one edge. In this graph, let's add one edge. Let's add BA edge. This edge, let's add edge BA. Okay, this BA, this edge, let's add. So let me add this edge. Means I am adding this edge. Now tell me, here what is the number of connected, strongly connected component? That is also 1. Here also 1 and here also 1. Okay, so it can remain unchanged, right? So here also 1, here also 1. You are adding one edge. This edge you are adding, this edge. Okay, very simple. So I can say that, yes, it can remain unchanged. May remain unchanged. Yes, correct. Can it reduce by more than 1? Cannot decrease by more than 1. Cannot decrease by more than 1. No, 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 no. See, actually, it can decrease a lot. Okay, let me tell you, it can decrease a lot. Just consider this graph. Please consider this graph. Okay, consider this graph. A, B, C, D, E. Consider this graph. How many strongly connected components? Tell me how many strongly connected components? 5. How many strongly connected components? Total 5. Total 5 strongly connected components. Tell me which edge I add such that one edge I will add and it will become 1. It will come down to 1. It will come down to 1. See, it will come down to 1. Number of strongly connected component, it can become 1 very easily. Very easily you can make it 1. Very easily you can make it 1. This is your original graph. Your original graph is this. You can decrease A, B, C, D, E. This is your original graph. You can bring, okay, by adding one edge, just add one edge, it will bring down to 1. Just add one edge. Okay, just add one edge, it will bring down to 1. This edge you add, and now number of, now how many? Only 1. From 5 to 1. Only one edge I am adding. Can you make it 2? Can you make it 2? Which edge I add such that it will become 2? 2 components I will get, such that I will get 2 components. If I do this, then I will get 2 components. If I do this, how? Okay, I want 3 components. I want 3 components. In this graph, I want 3 components. Is it possible? In this graph, I want 3 components. Is it possible in this graph? If I add, which edge should I add? Which edge should I add? C to E. C to E. No, this edge will not do. No, this edge will not do. C to E will not do. E to C. E to C. Yes, now I have 3 components. If I do, okay, if I do this E to C, now you can notice I have 3 components. This. Total 3 components you have. And here you can notice total 2 components you have. Very simple. So can you notice you can bring down to anything? Yes or no? Is this clear? You can bring down the number to anything. So cannot decrease by more, okay, more than 1? No, it can. Cannot decrease by more than 2? It can. Basically, it can go up to any number. Okay, is this clear to everyone? Please tell me. So note. So remember, if you have a directed graph, if you have a directed graph G plus 1 edge, okay, let's assume you have a directed graph G. In this directed graph G, let's assume number of strongly connected components is K. Okay, let's assume number of strongly connected component is K. Okay, now if you add one more edge, okay, you have this G in which number of strongly connected component is K. Now G plus 1 edge, if you do this, then number of strongly connected component, what can I say about them? They cannot increase. So okay, they cannot increase, but they can decrease. They can never increase. If you add one edge, you are adding one edge, then they cannot increase, but they can decrease. They can decrease to 1. Is this clear? Please tell me, the concept is clear or not? So what happens when you add one edge? We have already seen. This we have seen. This we have seen. Okay, and this we have seen. Also this we have seen. These concepts we have seen. So this is your concept of strongly connected component. Please tell me, is this clear? Concept of strongly connected component. Anyone has any doubt in this? Crystal clear. Can I say crystal clear? Is it crystal clear? Okay, very good. So this is the definition. You can notice. Now, what is a strongly connected graph? A directed graph is strongly connected. When can I say a graph is strongly connected? Tell me, what do you think? A directed graph, you have a directed graph. When can I say this graph is strongly connected? When can I say this graph is strongly connected? When you have only one strongly connected component. Yes or no? Okay, when you only have one strongly connected component, I can say there is a path between every two vertices. Okay, every two vertices you take, every two vertices are strongly connected. Every two vertices are strongly connected. Every two vertices. So this is the definition of a strongly connected directed graph. For directed graph, what is the strongly connected graph? Strongly connected digraph, directed graph. So when can I say a graph is strongly connected? I can say that very simple. You can use this definition. Number of strongly connected component is equal to 1. Okay, either you can use this definition, you can use this definition, or you can use this definition that every pair of vertices, any two vertices you take, every pair of vertices are strongly connected. Are strongly connected. Every pair of vertices are strongly connected. Every pair means number of strongly connected component will be 1. Okay. For example, this graph, if you notice, this graph is strongly connected. This graph is strongly connected. This graph is strongly connected. This graph is not strongly connected. What is the number of strongly connected component here? Number of strongly connected component 1. And what is the number of strongly connected component here? Number of, okay, so you can notice this is a cycle. So, okay, this is a strongly connected component. This is a strongly connected component. This is a strongly connected component. So this is 3. So the definition is very simple. Let's see this one. A, B, C. Is this strongly connected? Can I say this is strongly connected graph? Yes, this graph is strongly connected graph. SCG, strongly connected graph. Yes, this is strongly connected graph. Now you notice one more thing. This is also a strongly connected graph. This is also a strongly connected graph. Agree? In this graph is also a strongly connected graph. You can check it out. Okay. Next. This graph is also a strongly connected graph. All these graphs are a strongly connected graph. No, these are not isomorphic. How they are isomorphic? Sandeep, how many edges you have here? 4 edges, 3 edges. Here, total 4 edges. Second and first. How see, here you have 4 edges, here you have 3 edges. Okay, so these are strongly connected graphs. Actually, normally, let me tell you. Okay, no, this is what we think. Okay, note. We think, we visualize. Remember, we visualize strongly connected component as a cycle, as a directed cycle, as a directed simple cycle. This is how we visualize. This is just a visualization. Okay, like if I say, for example, if I say that a strongly connected component is this A, B, C, D, then how can you visualize? How can you visualize this? You can visualize this like this. Like this, you can visualize. Okay, are you getting my point? This is how we visualize. So we visualize this strongly connected component as a directed simple cycle. But remember, it need not be directed simple cycle. You can notice, for example, here also, this is also a strongly connected graph. Only one strongly connected component you have. One strongly connected component you have. Here also one strongly connected component. Here also one strongly connected component. Here also one strongly connected component. Okay, so very simple, these things. So this is how we visualize the strongly connected component. Okay, let's see this question. Please tell me everything. Like, is this, first of all, you tell me, is this strongly connected graph? This graph, is it strongly connected? So find number of strongly connected components. What that will be? Number of strongly connected component. How to find? Go systematic. Don't go random. If you will make mistake. Find strongly connected component of 0. Let's find out a strongly connected component of 0. So that will be 0, 1, 2, 3. That will be 0, 1, 2, 3 because there is a cycle. See, there is a cycle. So 0, 1, 2, 3. And you can notice that nothing else. So this is strongly connected component we got. Okay, we got this strongly connected component. Which is the strongly connected component of vertex 5? Vertex 5. That will be 5, 4, 6. You can notice that will be 5, 4, 6. So this is a strongly connected component. You can notice this is a cycle. This is a cycle. And this is another strongly connected component. Okay. So finally, this is also another. So finally, I can say number of strongly connected component is 3. Total 3 strongly connected components you have. So is this a strongly connected graph? Can I say this is a strongly connected graph? Is this a strongly connected graph? No, this is not a strongly connected graph. Let's see this one. How many? What is the number of strongly connected components? Quickly tell me. How many strongly connected components we have here? There are total 4. You can very easily see there are total 4. Okay, because you can notice this will be a component, this will be a component, this will be a component, this will be a component. Nothing else. So there are 4 components, strongly connected component. So this is also not a strongly connected graph. So everything we have seen. So remember, intuitively, we think of a strongly connected component as a cycle. Okay. So this is the complete thing that we have seen. Everything we have seen. So let's, should we take a break? So let's take a small break, and after the break, we will continue. Okay. Let's take a small break, just a small break for 3 minutes. Okay. Only for 3 minutes. I did not reject any opinion. Okay. I just wanted to take 3-minute break. Hi all, welcome back. So let's see now. For directed graph, what is connectedness? So we have already seen a strongly connected graph. When can I say a graph is strongly connected? If you have one strongly connected component. There is something called weakly connected graph. Like a directed graph is weakly connected. The definition is very simple. A directed graph is weakly connected if the underlying undirected graph is connected. The underlying undirected graph is connected. So remember, these are the two categories for directed graphs. These are the two categories for directed graphs. The directed graphs, I can say that these are the two categories. One are strongly connected. Okay, one are strongly connected. There is something called strongly connected. And one important class is weakly connected. These are not opposite of each other. Remember, these are not opposite of each other. The definitions are completely different, completely different. Strongly connected means number of a strongly connected graph means strongly connected component is one. Number of strongly connected component is one. And what is weakly connected graph? Means underlying. Remember, underlying undirected graph must be connected. Underlying undirected graph is connected. Graph is connected. Underlying undirected graph. Okay, so for this, we check the underlying undirected graph that must be connected. For example, okay, take this. Let me give you some graphs. A, B, C. Tell me, is this graph strongly connected or weakly connected? What do you think? This graph. Let's see another graph. A, B, C. This graph. Okay, let's see these two graphs. So tell me, is this graph strongly connected? No. Is this graph weakly connected? Yes. What is the underlying? What is the underlying? See, this is the underlying undirected graph. Underlying undirected graph. Just remove the direction. Just remove the direction. Remove the direction. Okay, just remove the direction. Like remove the direction. Remove the direction. So this is underlying undirected graph that is connected. This is also not strongly connected, but this is weakly connected. Let's see this question. Now tell me. Now tell me. Again, this is not strongly connected. This is weakly connected. This is strongly connected also. This is weakly connected also. Okay. This is strongly connected also. This is weakly connected also. This graph. Okay. Sandeep, don't write SCC. SCC means strongly connected component. Write SC means strongly connected graph. Or I can see, or I can write like this. If you don't, okay, let me write like this. A strongly connected graph, no. Weakly connected graph, yes. A strongly connected graph, yes. Weakly connected graph, yes. Okay, so like this you can write. Just write this G here. So you can notice a strongly connected graph, no. Weakly connected graph, yes. A strongly connected graph, no. Weakly connected graph, yes. Let's see this graph. Look at this graph. A, B, C, D. What about this graph? This is not weakly connected because this is clearly the underlying undirected graph is disconnected. You can notice. Remove the direction. See, remove the direction. Remove the direction. Now you can notice the underlying undirected graph is disconnected. Underlying undirected graph is disconnected. So this is not a weakly connected graph. This is not a strongly connected graph also. And this graph, so you can notice that, okay, all the categories, which category we don't have? Which category is not possible? You can notice every strongly connected graph is a weakly connected graph also. Yes or no? Every strongly connected graph is a weakly connected graph also. So these categories are possible. Like strongly connected graph, weakly connected graph, which categories are possible? If this is true, then this is also true. If this is true, then this is also true. But if this is not true, then this can be true, this may not be true. Okay, so these are the three categories possible. Is this clear? Three categories are possible. Every strongly connected graph is weakly connected also, because you only have one strongly connected component. So this is the simple idea. Look at this. This graph, is this a strongly connected graph? This graph, is it strongly connected? Yes, there is a cycle. See, there is a cycle like this. So this is strongly connected also, weakly connected also. This is not strongly connected, but this is weakly connected. Okay. Now, very important result. So this was an easy concept. Now, most important result. This is very important. Actually, why this is most important result for a strongly connected component? This is the most important result. The reason is, from this result, the question has come in almost all the good exams. Okay, in almost all the good exams. Good exam means the foreign university exams. Okay, so for example, like some exams are there, like GRE till 2022. This GRE computer science exam used to happen. GRE computer science exam till 2022. Okay, so in this exam also, from this topic there are many questions, and this topic is actually very important, but there is no question in the GATE exam so far. In the GATE exam so far, there is no question from this topic, from this result, but this result is very important because it is everywhere. Someday it will come, I can guarantee. Someday this will come in the GATE exam. Okay, anyway, let's see this. What is this? So what is this result for strongly connected components? So understand this, please understand this. What is that? See this. In directed graph, what you do, can you notice one thing? If you notice, strongly connected component is like a team. Okay, can you see every strongly connected component is like a family? Can you notice? Every strongly connected component, every strongly connected component is like a family. Yes or no? Is like a family. Is like a family. Correct? It is like a family. Every strongly connected component is like a family. For example, let's assume this is a family A, B, C, D. Then they are strongly connected to each other. See, they are strongly connected to each other. Yes or no? They are strongly connected to each other, and it is maximal. What is the definition of family? What is the definition of family? Family is also maximal, if you notice. What is the definition of family? Can anyone tell me? What is the definition of family? Let's assume that this is mother, this is father, this is boy, this is girl. Can I say this is family? Mother, comma, girl. Can I say this is family? Can I say this is family? This is not family. Family is maximal. Okay, something like this. Yes or no? This is the analogy. See, this is not family, mother, comma, girl. Basically, family is a maximal. I can say this maximal. This is family. I can say family is maximal. Maximal group of members who are strongly connected to each other. Okay, who are strongly connected to each other. Strongly connected to each other. And this family, this is the favorite dialogue of Dom, favorite dialogue of Dominic Toretto. Do you remember? Fast and Furious. Family. We are family. This is the favorite dialogue of Dom. Anyway, there is a movie. Fast and Furious. Anyway, so in that. So you can notice what is a family. Family is basically a maximal group of members. This would be maximal. A maximal group of members who are strongly connected to each other. Now, so this, if you notice, this strongly connected component is like a family. Okay, so for example, these are, now can you notice one more thing? Please notice one more thing. Let's assume this is the family. So this is your strongly connected component 1. This is strongly connected component 2. Is it possible? This is strongly connected component 2. This is strongly connected component 1. Like this is a family. This is maximal. This is a family. This is maximal. Is it possible that B, D are strongly connected? Is it possible? Is it possible that B, E are strongly connected? that they are strongly connected? Is it possible? Is it possible they are strongly connected? Is it possible? The answer is no. The answer is clearly no. Why? What is the reason? What is the reason? Because if they are strongly connected, if they are strongly connected, then this whole thing will be a family. There will be, okay, then this will become a family. Yes or no? Very simple. See, if they are strongly connected, if they are strongly connected, then automatically everything will be strongly connected, because they are strongly connected, because they are strongly connected. So everyone will become strongly connected. So you can notice that if they are strongly connected, then you will get a then they will merge. Then they will merge. The idea is, answer is no. Why? The answer is no. Why? What is the reason? Okay, because if, okay, so if they will basically merge, the idea is very simple. So the answer is no, because else they would merge. The answer is no. So answer is no. Else they would merge. Else they would merge and make single strongly connected component. Make single family or strongly connected component. So this is the idea. Now you can notice that every strongly connected component is like a family. So can I represent it by one family? Like, okay, what do you do? This is like a family. So you represent this by one vertex. What you do? You shrink it. These four vertices, you shrink them, and you, okay, represent them by one family F1. You represent them by S1, and you represent them by S2. You shrink them. Okay, these four vertices you shrink, and okay, you make one vertex. Okay, like it's like you shrink them and you make one vertex with one family, and you shrink them and you make one family. So this is the idea. What you do in a directed graph, if we shrink, okay, if we shrink each strongly connected component down to one single node, okay, and then draw, how to draw an edge between two of them, edge between two family, edge between two strongly connected. If there is an edge between some node in first to some node in second, okay, then we call the new graph, that you will get, the new graph, we will call it associated directed acyclic graph. I will tell you why. I will tell you the reason why this is associated directed acyclic graph. Why this is acyclic, I will tell you the reason. But this new graph will be called associated DAG. This new graph, we will call it associated DAG. Let's understand this concept. Let's understand. So for this, find associated DAG. Let's find associated DAG. For this graph, find associated DAG. Let's find. So this is your graph G. In this graph G, let's find out associated DAG. So what I will do, see, very, very simple. What I will do, you can notice this is a family. This is a strongly connected component. There is a cycle. So this is a strongly connected component. What I can say? I can say this is a strongly connected component. So let's call it S1. This is also a strongly connected component. Let's call it S2. And this is also a strongly connected component. Let's call it S3. Then what is the associated DAG? It simply means that you make families. S1 family, S2 family, S3 family. S1 family, S2 family, S3 family. Now, you can notice there is edge between from S1 to S2. Why? Because this person is friend of this person. Like I can say this person is related to this person. This edge is because of whom? Can anyone tell me? From S1 to S2, there is edge because of this. Because of this 2,4. Yes, very good, very good. Because there is 2 here. There is 2 here. There is 4 here. Because of these 2, this is the edge. Because of these 2, this is the edge. There is 2 here, there is 4 here. And you can notice there is edge from S2 to S3. There is edge from S2 to S3. And this edge is because of 6,7. Because of 6,7, this edge we have. Is this clear? So finally, I can say that this is the associated directed. Can you notice this is acyclic graph? Can you notice this is acyclic graph? Can you notice this is directed acyclic graph? Did you understand this? Did you understand this concept? If we shrink each family, each strongly connected component, we shrink down to be one vertex. Okay, we shrink it to one vertex. And when do we put edge? Edge we put if there is an edge from some vertex in the first to some vertex in the second. Then this new graph we will call it associated DAG because it is acyclic. This new graph will be acyclic. Let's see this question. Find associated DAG. Let's find out associated DAG. For this, don't worry, I will answer all your doubts, but find associated DAG. So what that will be? Find associated DAG. Very simple. This is one family. You can notice this is one family. So I can say this is a family S1. This is another strongly connected component. This is another strongly connected component. So what will be the associated directed? Okay, so that will be S1, S2, S3. You can notice there is edge from S1 to S2. There is edge from S2 to S3. Or you can understand like this. You can understand like this. See, you can understand like this. Make one vertex for 0, 1, 2. Make one vertex for 0, 1, 2. Make one vertex for 3. Make one vertex for 4. Now you can notice that there will be edge. There will be edge from here to here because of 0 to 3. Because of this. So because of 0, 3 there is edge, and from 3 to 4 there is edge. You can notice this is you can notice this is directed acyclic graph. If you notice, there is no cycle. This is directed acyclic graph. Let's see this question. In this question, what will be the associated DAG? What will be the associated DAG for this? That will be a single vertex. That will be a single vertex 0, 1, 2. A single vertex. You will get a single vertex. Basically, you will get a single vertex. I can say this will be your associated DAG. If you call it S1, then this will be your answer. Okay, this will be the answer. So this concept is clear. Next, what about this? Find the associated DAG. Associated DAG. What that will be? Find the associated DAG. So again, you can notice that this is your strongly connected component S1. This is a strongly connected component S2. This is a strongly connected component S3. This is a strongly connected component S4. So what is associated DAG? That will be like this. A, B, C, D. There will be F. There will be G. There will be H. There is H from this to F. There is H from F to G. There is H from F to H. Also, there is H from G to H. Okay. So can you notice this is also directed acyclic graph? If you notice, this is also directed acyclic graph. Is this clear to everyone? This is the associated DAG. Next, what about this? What is the associated DAG for this? What is the associated DAG for this? This itself. Okay, associated DAG, same. G itself. I can say G itself. G itself is the associated DAG because this is already DAG. If you notice, this is already a directed acyclic graph. So actually, these are the, if you notice, these are the strongly connected component S1, S2, S3, S4. So these are the strongly connected component. You will get the same. This G itself you will get. What about this? This is your graph G. Find the associated DAG. Find associated DAG. What that will be for this? So here you find the, first you find, why no? First you find the strongly connected component. This is a strongly connected component S1. There is a cycle here. So this is a strongly connected component S2. This is a strongly connected component S3. This is a strongly connected component S4. This is a strongly connected component S5. S5. This is S6. This is S7. So total you have 7 vertices. Yes or no? Total you have 7 vertices. So in this total you will get 7 vertices you will get. Total you will get total 7 vertices you will get. So the answer that you will get will be like this. See, associated DAG. The answer you will get will be like this. S1 from S2 to S2 there is S1 to S2 there is age. There is age. From S4 to S5 there is age. From S6 to S7 there is age. And from S7 to S5 there is age. And there is S3. This will be the answer. Yes or no? Can you notice this is also DAG? Can you notice this is also directed acyclic graph? This is also DAG. Clear? Is this clear to everyone? Anyone has any doubt in this? Let me know. So this is the final point. If you shrink, you will get a, remember, you will definitely get a DAG. Remember, you will definitely get a DAG. Why? What is the reason? This is my question. Why we get DAG? Why we get directed acyclic graph? When we shrink, basically, okay, why we get directed acyclic graph in the previous problem? In the previous problems, why we get directed acyclic graph? The concept is very simple. See, if you don't get directed acyclic graph, first of all, you notice every vertex is what? First, you tell me every vertex is what? Every vertex is what? A strongly connected component. Every vertex is a strongly connected component. This you already know. And a strongly connected component is maximal already. And this is maximal already. This is already maximal. You cannot make it bigger. You cannot make it bigger. Now, if you don't get, if you get cycle, by chance, if you get cycle, then what is the problem? Like if you get this type of cycle, let's assume this type of cycle you get. If you get this cycle, then what is the problem? Then you can merge into one. If you get this cycle, then what is the problem? The problem is that now you can, okay, if you get this cycle, what it means? It means these were not maximal. It means if you get cycle, then it means these were not maximal. These were not maximal. There is a contradiction. These were not maximal. So contradiction. So you will definitely get a directed acyclic graph. Okay, if you get a cycle, it simply means that these were not maximal. These were not maximal. These could have been merged. Could have been merged in original G. These could have been merged in original G. I can say these were not maximal in original G. So there is a contradiction. Okay, please tell me, is this concept clear? So remember, this is a very simple idea. If you shrink each strongly connected component, down to one vertex, and you put an edge from some node to then some node, then this resulting graph will be a directed acyclic graph. And the reason is very simple. What is the reason? The reason is very simple, that if you have a cycle of strongly connected components, then you would have merged them all to single. Okay, so finally, this is the line. This is the statement. I can say every directed graph is DAG of its strongly connected component. This is the statement. This is the theorem. Every directed graph is directed acyclic graph of its strongly connected component. Did you understand this? Every directed graph is a DAG of strongly connected components. Okay, it is DAG of strongly connected components. I hope this concept is clear. Very simple concept. Like, what is the associated DAG now for this graph? What is the associated DAG? What that will be? What that will be? You can notice this is your S1. You can notice this is your S2. You can notice this is your S3. And so this is not a cycle. So you can notice this is S4. What about A, B, C, D? There is no cycle. What about A, B, C, D? What about A, B, C, D? See, you, okay. So yes, there is a cycle. So this ABC we have. What about AD? What about AD? No. Okay, so I can say that this will be a strongly connected component. See, this will be a strongly connected component. I can say this will be S5 and this will be S6. This will be S6. This will be S6. So total 6 vertices you will have. ABCF. Oh, right. Oh, right. ABCF. Oh, right. Okay. So ABCF. Yes, very good. Okay. So actually always do like this. See, always do like this. If you don't want to make mistake like me, okay. If you don't want to make mistake like me, then always do like this. Always do like this. Okay. Let's find out the strongly connected component of A. Always do like this. If you don't want to make a mistake, always do like this. Let's find out what is the strongly connected component of A. You can notice A will be there, B will be there or not. From A to B we have, from B to A also we have. So B also will be there. So B also will be there, C also will be there. So okay, B also will be there, C also will be there. B also will be there, C also will be there. Now think about it. D will be there or not? Think about it. D will be there or not? There is no path from D to A. Check it. There is no path from D to A. So D will not be there. F will be there or not? F will be there or not? There is path from F to A. There is path from A to F. There is path from F to A. There is path from A to F. So F will be there. Okay. Tell me, H will be there or not? H will be there or not? No, because there is no path from A to H. There is no path. So this is the idea. Okay. Always do like this. Always do like this. So I can say that this will be your strongly connected component S4 and this will be your strongly connected component S5. So number of strongly connected component, that will be 5. So in the associated DAG, you will have 5 vertices: S1, S2, S4, S5, S3. So you can notice from S2 to S4, okay, and from S1 to S4, and you can notice that from S4 to S5, from S4 to S5, and from S4 to S3, S5 to S3. So this will be your graph, correct? Yes or no? This is S4, from S4 to S5, from S4 to S3, from S5 to S3. Yes, so this is correct. Okay, this is underlying, this is the associated DAG. You can notice this is DAG. You can notice this is directed acyclic graph. Okay, let's see this question. This is a university exam question. Sandeep is saying, sir, so one edge in DAG need not be actually one edge in actual graph. How are you saying that? Which edge are you talking about? Sandeep, which edge are you talking about? S4 to S5. There is edge from S4 to S5, right? See this S4 to S5, this edge, look at this edge. In actual graph, look at this edge. Look at this edge. This is yeah, that is fine. I'm not getting your doubt. See, this is your okay. You have edge from S4 to S5 because of this or because of this. At least one. Is this clear? Sandeep? Yes, yes, of course. At least one must be there. At least one edge must be there. Let's see. Let's see this question. This is a university exam question. So find associated DAG. So what the answer will be? Find associated DAG. So first you find the first you find the strongly connected components. So okay, do systematic. Do systematic. Let's find out the strongly connected components of A. So A will be there. What else? You can notice this cycle. You can notice this cycle. So A will be there, B will be there, E will be there. Can I add C? Okay, can I add C? See, from A to C you have, but from C to A, can you go from C to A? Can you go from C to A? No, you cannot go. You cannot go from C to A. You cannot go. What about D? Can you go from D to A? Can you go from D to A? No, you cannot go. Okay, so you cannot go. So I think only this will be there. Okay, so A, B, E. This will be your graph. So this will be a strongly connected component 1. Next, what is the strongly connected component of D? What is the strongly connected component of D? D will be there. You can notice this cycle. Notice this cycle. Notice this cycle. So DGH, DGH. Can I put I? Tell me, can I put I? There is path from D to I. There is path from I to D. So yes, I can put I. Okay. And you can notice that. You can notice this also you can put. Because of H, you can put HFI. You can put F also. So you can put F also. Okay. So finally, this graph you got. Nothing else you can put. Nothing else. This is your strongly connected component 2, and this is strongly connected component 3. This is the strongly connected component 3. You can just check it. Okay. So finally, this C, it will only have C. No other vertex can basically no other vertex is strongly connected to C. So finally, your number of, I can say number of strongly connected component is 3, and the graph you will get will be like this: S1, S2, S3. The graph you will get like this. From S1 to S3 there is edge. From S1 to S3. From S1 to S2 also there is edge. Next, from S3 to S2 there is also edge. Nothing else. Okay, nothing else. Remember, in the exam they will give you this. They will not give you this. Actually, what they will give you, they will give you this. In the exam, they will give you, they will write the vertices. S1 means ABE. S1 means ABE. And you can notice S2. S2 means DG, this DGHIF. And S3 means C. So in the exam, they will give you like this. This is the DAG. You can check, this is the directed acyclic graph. Okay, so that's it. Tell me the answer for this. Quickly tell me. How many strongly connected components you have in this graph? So can you take it as a homework? Like, actually, this is very simple question. So you can notice this will be one strongly connected component. This is one strongly connected component. You can check. You can check. This is one strongly connected component, S1. What next? What is the next? So you can notice that This is another strongly connected component as 2, and this is another strongly connected component as 3. This will be S3. So total 3 components you will have. Okay, number of strongly connected component, that will be 3. Yeah, it is already marked. Okay, so let me remove. Okay, actually an associated DAG, what that will be? Associated directed acyclic graph, what that will be? That will be like this. That will be like this: 0 1 2 3 5 4 6 7 4 6 7. So finally what you will have? From 4 6 7 to this you will have, from 5 to this also you will have, from 5 to this also you will have, and from 5 to this also you will have. Okay, this is your DAG. You can check, this will be your DAG. Okay, so the answer will be 3. What is the answer for this? Number of connected components. How many connected components in this graph? The answer is only 1. This is undirected graph. Remember, this is undirected graph. This is your undirected graph. So because this is undirected graph, so this is your one component, only one component you have. What is the answer for this? Again, this is undirected graph. Okay, this is undirected graph. Because this is undirected graph, how many components you have? Total 2 components you have. This question you can take as homework. Okay, so for this question you have to find number of strongly connected components and also associated DAG. Okay, so you can take this as a homework because many questions we have done. Yes or no? This is another homework. Already many questions we have done. So let's see this next topic. This is a very short topic, very small topic. Let's quickly see this. Let's see this. Adjacency matrix. What is the doubt, Akash? Which question? Is this question? This question? Yes, there will be 2. There will be 2. Okay, here you will have 2. Basically A, B, C, D, E, F. So there are 2 components. A, B, C, this is one component, and D, E, F, this is another component. So this component, this component. Total 2 components you have. Okay, next, let's see. Next, let's see this concept: adjacency matrix, adjacency list. Have you studied this concept in the data structure and algorithm? Have you already studied adjacency matrix, adjacency list? Did you study this? Tell me, in the data structure, did you study this? Sachin sir. So did Sachin teach this? Not yet. Okay, it will come. Don't worry, it will come. In the algorithm and data structure, when you study graph algorithms, like minimum spanning tree, Dijkstra algorithm, okay, shortest path algorithm, there it will come. This will come to, okay, this will come. Don't worry. So what is this adjacency matrix and what is this adjacency list? These are representation of graph. These are the representation of graph in a computer. In a computer, how to represent graph? Representing graphs in computer. In computer, if you want to represent graph, you cannot represent like this. Just think about it. Can you represent like this in your memory? Just think about it. In your memory, is this graph will be there? Like in a memory. Like for example, this is your RAM and this graph is there. Is it? Does it happen like this? Does it happen like this? No. Okay. So this is your graph. In memory, in computer, how to represent this? In computer, you can represent this in 2 ways. This graph you can represent in 2 ways. One way is adjacency matrix. You can create a matrix like this. You can create a matrix ABC, ABC, and you can notice there is age from A to B. There is age from A to B. So I can say 1, I can say 0. There is age from A to B. So there is age from A to B. So there is 1. There is no age from A to A. Okay. And there is no age from A to C. So 0. There is age from B to C. And there is age from C to A. So this is your adjacency matrix. This is the adjacency matrix. You can notice there is edge from A to B, but there is no edge from B to A. There is edge from A to B, but there is no edge from B to A. There is no edge. So you can notice from B to A there is no edge. Okay, very simple. So we put 1 when there is edge. We put this 1 because there is edge from B to C. We put this 0 because there is no edge from C to B. So this is the concept of adjacency matrix. Another is adjacency list. Either you can represent in your computer, either you can represent as a matrix in computer, or you can represent as a list, adjacency list. What it will do? So you will make an array, you will make a list, you will make a list. These are the vertices ABC. These are your vertices ABC. Now just write this A is adjacent to whom, like this A, this is adjacent to whom, this is adjacent to B, from A to B, from B to C, and from C to A. That's it. This is adjacency list. We call it adjacency list representation. So there are two representation: adjacency matrix, adjacency list. Let's see this graph. For this graph, what will be adjacency list? This is an undirected graph. Your graph is undirected graph. So for this graph, what will be adjacency list? Means, for example, so there will be array. Remember, adjacency list means there will be an array. This type of array you will have. So in computer, what you will do? In computer, you will make an array. This array you will make. This array you will create. A, B, C, D, E. This array you will create. And then this linked list you will create. Okay, this linked list you will create. This linked list. Okay, this linked list you will create like this. So you can notice A is adjacent to B, C, E. A is adjacent to B, C, E. A is adjacent to B, C. So B, C. B is adjacent to A. So B is adjacent to A. C is adjacent to AED. C is adjacent to AED. E is adjacent to ACD. E is adjacent to ACD. And this D is adjacent to EC. D is adjacent to EC. Is it clear? Adjacency list. Very simple. For every vertex, you create an array. You create one array and just put the vertices which are adjacent. Put the vertices which are adjacent in a list. For example, this graph. For this graph, what will be the adjacency list? So you will make a list. You will make array. This array you will create. Okay, in this array, you can notice that A is adjacent to whom? A is adjacent to E, D, B, C. So A is adjacent to B, C, D. B is adjacent to B. You can notice because of this self loop. Because of this self loop, B is adjacent to B. B is adjacent to D. B is adjacent to D. And you can notice C is adjacent to C because of self loop. C is adjacent to E, and C is adjacent to A. You can notice D is not adjacent to anyone. D is not adjacent to anyone. Empty list. E is adjacent to BCD. Is this clear? Let me know. Next is adjacency matrix. What is this? This is like a matrix. Very simple. The concept is like a matrix. So if your graph is this, then what you can do? You can create a matrix. You can create a matrix like this. You can create A, B, C, D, A, B, C, D. This type of matrix you can create. What you will do? You will create this type of matrix: A, B, C, D, A, B, C, D. The same order. You can fix this order. Fix this order: A, B, C, D, A, B, C, D. Now you can notice that A is adjacent to B, C, D. So you can note 0, 1, 1, 1. A is adjacent to B. So 1. I am putting 1 because A is adjacent to B. And you can notice that D is adjacent to A. And D is not adjacent to anyone else. So 0, 0. So anyway, this is the idea of adjacency matrix. This concept you will again study in the algorithm subject. But is this clear? See, this 0 means these C, D are not adjacent. C comma D, they are not adjacent, so 0. C comma B are adjacent. C comma B, they are adjacent, so this is 1. Is this clear? Like this is your graph. For this graph, adjacency matrix will be like this: A, B, C, D, A, B, C, D. Fix the order. Fix the order. Remember, always fix the order. Fix one order. That is your choice. How to fix? Normally alphabetical order. By default, you have alphabetical order. Okay. So your graph, your adjacency matrix will be this. This is your GATE 1987 question. What will be the answer? Adjacency list representation of this graph. What is the adjacency list representation? So this is the answer. Oh, I did not take the answer. Okay. So for this, what will be the answer for this? Let's check it out. So you have 5 vertices. So you will create a list like this. You will create an array. There are 5 vertices. 1, 2, 3, 4, 5. So this list you will create now. Okay. So this list you are going to create like this. So this 1 is adjacent to 2, 3, 5. 2, 3, 5. This 2 is adjacent to 1, 3. This 3 is adjacent to 1, 4, 5. This 4 is adjacent to 3, 5. And 5 is adjacent to 1, 3, 4. This will be your adjacency list. And what will be adjacency matrix? You can create adjacency matrix also very similar. Okay. Like this, you can create an adjacency matrix. Let's see this next question. We have to find adjacency matrix. This is GATE 1988 question. 1 is 2, 3, 5. 1 is 2, 3, 5. Oh, 1 is 2, 3, 5. Okay. So this will be 2, 3, 5. Okay, let's see this. Adjacency matrix we have to create for this directed graph. This is a directed graph. Very simple. P1, P2, P3, P4, P5. Very simple. Just fix this order. Fix this order. Now you can notice. From P1 to P1, there is no edge. There is no self loop. From P1 to P2, 1. Because from P1 to P2, there is edge. From P1 to P5, there is edge. So I can say like this. From P2 to P2, there is no edge. There is no self loop. From P2 to P4, there is edge. From P2 to P4. So like this, you can fill. Anyone has any doubt? Can you fill it? Can you fill this table? Please let me know. This is your TIFR question. This is the TIFR exam question. Let's solve this. This is a nice question. The definition is given to you in this question. Already the definition is given that this is the adjacency matrix of undirected graph with 6 vertices. The rows and columns are indexed by vertices of the graph. Entry 1 means they are connected by A's. Connected by A's. Entry 1. Entry 1 means connected by A's. Else 0. The same order you are taking for rows and columns. The same order. You are taking the same order for rows and columns. The same order you are taking for rows and columns. Means if this order is A, B, C, D, E, if this is A, B, C, D, E, A, B, C, D, E, F, then this order is also A, B, C, D, E, F. Can you notice this beauty of this question? Every detail is given. Yes or no? Every detail is given in this question. Every information is given in this question. This is the beauty of TIFR question. These TIFR GATE exam question, these are very nice questions. TIFR, GATE exam. These 2 exams are excellent. Okay, let's see. So which will be the answer? Which will be the answer? How to check? What do you think? What should I do? What do you think? What should I do? Let's find degree. Very good, very good. Excellent. Find the degree sequence from this. Find the degree sequence from this. Let's find degree sequence from this. What will be the degree sequence? Tell me. What is the degree of A? So here I am writing, okay, what is the degree sequence? Like this vertex A, what is the degree of A? That is 2. Degree of A is 2. Degree of B is 2. Degree of C is 3. Degree of D is 2. Degree of E is 2. Degree of F is 3. So the degree sequence is Degree sequence is 3 3 2 2 2 2. 3 3 2 2 2 2. This is the degree sequence. Which option is gone? Which option is gone? Tell me. 1 comma 4. This option is no no no. 1 how 1 comma 4 are gone here? 1 comma 4 is not gone. Is there any option which is gone or no option is gone? Option 3 is gone, I think. Option 3 is gone. Option 3 will be gone. Okay, 3 out. 3 is cancelled. So 3 is out. Okay, let's see what I can do. What else I can do? So degree sequence I can do. Okay, so what else? What else? Now notice these degree 3 3, are they adjacent? Just check it out. Degree 3 3, are they adjacent? Degree 3 3 vertices, are they adjacent? Check it out. Are they adjacent? Like this vertex C, this is degree 3 vertex, and this is degree 3 vertex. Are they adjacent? C comma F, are they adjacent? C comma F, yes, they are adjacent. You can notice they are adjacent. Degree 3 vertices are adjacent. Correct or not? Degree 3 vertices are adjacent. So which is gone? Degree 3 vertices are adjacent. So which is gone? So this fourth is gone. Fourth is gone. Now what else I can do? Still two options are there. What should I do? Okay, now two options. Let us see what to do now. You have two options. So here you notice anyone tell me what else can I think, like what else can I do? So two options are gone, still two options are remaining. Still we have two options that are remaining. So what creative technique we can create, we can do? What is the creativity we can do? Let's see some difference between this structure 1 and structure 2. Let's see some difference between these two. Let's see some difference between these two. Is there any difference or no? First of all, is there any difference or no? A, B. So degree 3 vertices, remember, okay, see this, please notice here. Please notice here that these degree 3 vertices, which are calling, we are calling them C comma F. We are calling them C comma F. Degree 3 vertices, we are calling them C comma F. We are calling them C comma F. Degree 3 vertices, we are calling them C comma F. Okay, so here we have C, F, and there are two vertices like this. Okay, there are two vertices like this, and there are two vertices like this. And in this graph, what we have? In this graph, we have CF. There are two vertices like this. There are two vertices like this. Actually, both these graphs are isomorphic. They are isomorphic, right? This is your C, this is your F. This also has 3, this also has 3. 2, 2, 2, 2. They are actually isomorphic. If you make it there, these two graphs are basically same. These are actually basically same. So if they are same, then if they are isomorphic, then you can say which of the below graph has the above adjacency matrix. Then the answer will be this also, this also. Or answer will be first and second. Okay, both of them. Because actually you can notice they are isomorphic. Notice they are isomorphic to each other. 1 comma second, they are isomorphic to each other. And because they are isomorphic and label is not given, please understand, label is not given. They are isomorphic. There is no labeling. Labels are not given. You can notice labels are not given. So they are isomorphic, 1 and 2. So I can say 1 and 2, they are isomorphic. So both will be the answer. Okay, 1 and 2, both will be the answer. Nikhil, this is what I'm doing. See, 1-to-1 mapping we are doing. 3 degree vertices, we are calling them C comma F. We are calling them C comma F. You can check both 1 comma 2 are same. Nikhil, vertex 1 comma 2 are same. Actually, this option 1, option 2, they are exactly same, these two options. Okay, so that's it now. So that's it. So this is your graph theory. We have seen everything. So this is a nice question. You can just check it out. But actually, option 1 comma option 2, they are basically same. Now, so this is your graph theory. This is your discrete mathematics. Finally, discrete mathematics is over. Okay, a lot of things we have seen, but I hope you enjoyed it. Like, okay, did you enjoy discrete mathematics course? Did you understand everything? Like, okay, we started from propositional logic, to graph theory. Every concept we have seen, every concept. Remember, if there is a small concept, if there is some small concept remaining, then you don't have to worry about it. We will cover in the practice session. Okay, some small concepts are remaining. Those concepts we will cover in the practice sessions. After the syllabus is over, in the September, once the syllabus is over, for the next 4 months, we will do practice and revision. At that time, we will cover if any small topic is remaining. Okay, if any small topic is remaining, everything we have covered. But of course, small topic, one question. Okay, some 1 to 2 question, maybe that, okay, somewhere that can be remaining. That we will cover. So you don't have to worry about it. So please don't worry for any topic, for any small topic which we did not cover. Don't worry about it. We will cover in the future. But this is the discrete mathematics course. Everything we have seen. So please let me know. I hope this course, yeah, Saurabh is saying that improved our analytical skills. Yes, this discrete mathematics is a very nice course. It will improve your analytical skills very much. Okay. Yes, Yuvraj, what you are talking about, I will discuss it. We will do complete analysis of adjacency matrix. Recorded video will be there. See, this is adjacency matrix complete analysis. This we will do. Adjacency matrix complete analysis we will do in a separate. I will record this video in a recorded video. I will record a video. Okay, don't worry about it. So what I'm saying is, don't worry about any topic, any small topic. You don't worry about it. I will cover. You don't have to think. Okay. So this is your discrete mathematics course. This is complete. Graph theory, combinatorics. In combinatorics, we have done more than 500 questions. Did you see? In combinatorics, more than 500 questions we have done in the class. In the class itself, these many questions we have done from combinatorics. Every variation, every theorem, every proof, every idea, every concept, everything we have seen. And so this is the end of discrete mathematics. Today I will share one feedback form. Okay, one feedback form for discrete mathematics I will share. Please, I request you to fill it. Okay, please fill it. Give 5 minutes, only give 5 minutes, fill the feedback form. Okay, please just spare 5 minutes and fill the feedback form, and also give your feedback. Okay, give your honest feedback, like detailed feedback. Give your feedback on the GoClasses website on the discrete mathematics course. Write your review. Okay, so in the discrete mathematics 2023 course, write your review. Okay, so if anyone has any doubt, you can ask. Please let me know. Do you have any doubt? Do you have any doubt? Let me know. In today's class, any doubt? Yes, Arpan, what is the doubt? Hello, Arpan.
Yes, sir. Am I audible?
Yes.
So I had a very small doubt, which is, so in the TIFR question, when we were calculating the degrees, so in which part did we get to know that the three degree vertices will be adjacent? So I did not understand that one.
This vertex C has degree 3. This vertex F has degree 3. You can check that they are adjacent. You can notice C comma F. C, this is C. Look at this. This is C. This is F. Are they adjacent? Look at them. Yes, they are adjacent. This one indicates that C comma F. This one This one indicates what this one is indicating.
That there is an edge between C and F.
Yes, so C comma F and C comma F, these are the 3 degree vertices. This means they are adjacent. So it means 3 degree vertices are adjacent. Because
Yes.
of this one. This one is telling us that C comma F are adjacent. Similarly, this is also telling us that C comma F are adjacent. You can notice C, F, they are adjacent. C, F. Okay.
Yes. So,
Is this
and
clear?
yes, sir. And one more thing was that, so in the last part, if we had confusion with whether option 1 and option 2 will be isomorphic, so in using this technique, can we also derive the adjacent vertices of the remaining vertices apart from the C and F? Then we can get an idea of which vertices were adjacent with which one. Like, can we use that technique? Will it be very viable?
See this option number 1 and option number 2, these are exactly same graph. These are exactly same graph. You have 3 degree vertices. On one side you have 2 vertices, on one other side you have 2 vertices. Similarly here, you have this 3 degree vertices, and on one side you have 2 degree vertices, on another side you have 2 degree vertices. Option 1 and option 2, these are isomorphic. Because they are isomorphic, they are exactly same. This and these two graphs are exactly same. They are exactly same. So for both of them, you can create this adjacency matrix. For both of them, this adjacency matrix you can create for both of them. Okay.
Exactly.
In the adjacency matrix, remember, order does not matter. You fix one order because order does not matter. These adjacency matrices are same. If I give you A, B, C, okay, this is your graph. Let's assume this is your graph. Now for this graph, these adjacency matrices are same. In the adjacency matrix, the order does not matter, but you fix one order. ABC, ABC, if I fix this order, then I will get 0, 1, 0. Okay, I will get 0, I will get 1, 0, 1, and I will get 0, 1, 0. This adjacency matrix is exactly same as this adjacency matrix, like BCA, BCA. You fix one order, just fix one order. So BCA, so I can say this will be 1, 1, 0. Sorry, this will be 0. Sorry, this will be 0, 1, 1, and this will be 1, 0, 0, and this will be 1, 0, 0. Okay. So like this. So both are same. So in the adjacency matrix, both are same. These are same adjacency matrix. They both of them are telling you the same graph. They are denoting the same graph. So the order does not matter. You fix one order. Just fix one order. Okay.
Exactly. Got it, sir.
Nikhil, we will have a separate video for Peterson graph. There will be separate video for Peterson graph. There will be separate video for these concepts. Basically, these are the concepts that will have separate videos. Okay, these small concepts which are okay, small concepts which will be recorded. Even if there is a single question, we will record it. See, there is a single question. Even if there is a single question, we will record it. Okay, so these concepts, like for example, your Peterson graph. This Peterson graph we will record in a separate video. There is a line graph. This we will record in a separate video. There is a concept of adjacency matrix analysis. This adjacency matrix analysis, complete analysis. This we will record in a separate video. Okay. So all these concepts we will record in a separate video. All these things. Some other concept, if there is any other concept, we will record. Don't worry. Any doubt, anyone? Any other doubt, anyone? In this graph theory? Okay, thank you. Thank you, everyone. So I will share the feedback form. Okay, please fill the feedback form. Okay, this is very important because we take your feedback very seriously. Okay, like every feedback that you will give, we will go through it and we will consider. Okay, so write your feedback. Honestly, you write your feedback and also write your review on the Go classes Discrete Mathematics 2023 course. Okay, thank you, everyone. Thank you.